In this video, I'm going to show you how to uh, take this program into a real machine, and I'm going to take you through every necessary amendments that might arise onto the initial program. Centrally, you need to know that whenever you are programming a real machine, your I1, I2 until whatever amount of uh, inputs and outputs need to correspond to the ones that you are actually programming onto your PLCs. So this PLC theoretically was correct, but it might differ when now we have to program a real machine. The most important thing when it comes to testing is that you need to know whether your inputs are currently switched on or off. So now I need to, my aim now is to identify the nature of my inputs, whether they are normally closed or normally open. And one of the things that I need to be careful of is whether that input is normally closed or it's currently pressed or not, because if it is currently pressed, it means the machine is bound to move in an opposite direction, or it would execute an unintended process. Therefore, when I observe on my machine, I can see that my I1, the machine is on its maximum position, the highest position. Therefore, I1 is pressed, and then I2 is not pressed, and they are both in the same axis. Therefore, I will simply change my I1 to I2 because I2 is not pressed. Right, the machine was on the run mode, so I have to take it out from the run mode so that it can download. Okay, so now let's observe what will happen with I2. If this is a normally closed, the machine will run. If it's a normally open, the machine won't do anything. It's a normally closed. That's why the machine is running. And it translates that I1 is also a normally closed. So I needed to stop the PLC there. So now I'm going to test I3. We have noticed that I1 and I2 are normally closed and they are on the same axis. Same applies to I3 and I4. They are on the same axis. And then there's no movement and the workpiece is at I3. So it can simply mean that I3 is a normally closed. Therefore, I need to shift my workpiece. Let me move it. Let me move my workpiece. Right, I put my hand. So as you can see, My I3 is normally closed. Therefore, I4 is normally closed as well. Then I'm back on the program. We've seen I1, the position of I1. I1 cannot start the machine like it used to on the theoretically. So now we're on practice. We're doing it practically. So I need to change my I4 to be an I7 so that because I'm intending to use the I4 before I get to this I4. So I need to keep in mind this was initially my I4. So the process needs to start using a different a different input, because I1, 2, 3 and 4, they are all currently used and they are normally closed. Therefore, the machine cannot start with a sensor. It needs to start using a push button. Luckily, the device we have has an extra push button connected on the machine, which is I5. So we still want to follow the similar diagram, but we need to also make amendments accordingly. This was supposed to delay 5 seconds before motor can move, and then as the conveyor belt moves to I4, then at I4 like this, at I4 the workpiece will execute I4. Then now I4 comes here instead of I2. Okay, I4 will stop the motor. I4 will bring down the puncher, but our Q3 is up and our Q4 is down. We need to swap those very quickly, and even the naming needs to swap very quickly. Okay, this is up. And this is down. Okay, and then I4 will call the downward motion, and then when it gets down, I2 will be active. So now everything gets to be changed according to the labels on the machine. I2 is then active. I2 will activate the upward motion that will in return be stopped by I1. So the reason why I used I7 because I needed to use I1. And then I1 through the preliminary latching that we have created here, which was activated by I2. I1 will then activate the backward motion of the conveyor, and then the workpiece will travel back until I3. Then at I3, the backward motion, we expect it to be resetted. Look at this. It's being resetted by that push button. Then it's wrong. We need I3 to reset our. So we can just simply copy and paste it like that. Okay. So now I5 starts the process, and then I4, I2, I1, I3. We know that the state of I1, 2, and 3, 4 are all normally closed. Therefore, we need to invert wherever they connect. On their first connecting point, we need to invert. This is the first connecting point of uh, I2. Another one is here, another one is there. So wherever I2 connects, we need to invert. Then I1 is also normally closed. Whenever I1 connects, we need to invert. I1 also with I3. And then I5, it's a normally open, so it has no problems. So now we have a 5 seconds delay in our process using the on delay, and you will see just now that the on delay is not an ideal timer to start the process, because when you're using a push button, that delay will never count. Look at this, it counts. When I release, it stops counting. Therefore, that on delay needs to change to become a rentative on delay. So a rentative on delay, oh Lord, okay, these minor mistakes you can do on PLC can be problematic, but it's fine. Right, like that. Okay, so now I have my rentative on delay. It has a delay. I can put that 5 seconds delay. Let me make it 3 now. 1, 2, 3. Okay, perfect. So this rentative on delay will replace the latch here. So because the rentative on delay can memorize that we need to delay before we start the process, unlike using the on delay, and then you need to always invert wherever necessary. Okay, so now let's observe one more time. Okay, the first sign of your program being correct is that nothing needs to move. Other than that, my I4 it looks pressed according to the state, but because of it's inverted, the blue points are the one that shows that there is nothing at I4, as you can see, but at I3 it's blue and here it's red. You only check the inverts, the state of the inverts. If the state of inverts is red, therefore it means it is pressed. I1, it's pressed because of when you look at where the position of the machine, you can tell that I1 is pressed. Right, then let me start the procedure. Okay, all right, as you have seen, the workpiece moved to I4, and then at I4 I4 activated the puncher to come down. As it gets to I2, then it went back. As it got to I1, then the backward motion was activated. So now, if I should remove the workpiece and put it again, what will happen? Let me move it. So you see the conveyor is still moving backward. So it means then there is a problem, and the problem is caused by this end here. It's permanently on, as you can see. The preliminary latch there, it's giving a constant what I can call this, a constant on the, therefore our uh, latch will always be activated. Then to simplify matters here, we need to change this end to become an end with an edge. They are almost similar, but the only difference is that end with an edge, as I might have said before, will only release a signal once until you activate again. While you're still pressed, the signal will never pass. So end with an edge, that's it there, okay? And then I need to invert accordingly. We invert there, okay? All right. So now it's still the preliminary latching, nothing has changed. Okay. Let's observe again. After 3 seconds, it goes forward, I4, and it goes backward. Then, when I move the workpiece, I realize that the machine doesn't keep on running, because here it's blue, it's no longer releasing the signal. So if I place the workpiece again, I don't have any issues, and I can restart the process. Okay, so for the fun of it, if I would want the machine not to stop immediately there at I4, because as you can see, it's pressing, it just quickly stops. If you want to prevent it from stopping like that, and you want it to at least stop at the center, like almost here, you will need to put a delay at I4. If you want it to stop there, then there will be a need for a delay at I4. Okay, a delay, you put a delay like this, an on delay. You don't need you don't need to use the orientative on delay in this case, because you stop at I4, you stop for a period of time, therefore the timer will be able to run, unlike in the case of an input of the I5. The timer couldn't run, because the moment we release our hand, so okay, we need milliseconds, at least 25 milliseconds. Okay, my keypad doesn't want to write. Numlock, okay, perfect. 25 milliseconds. So I5 is a push button, I4 is a sensor. When the workpiece is at I4, it presses the I4 until until Q4 switches on and Q4 comes. So there is no need for us to use the latch there. All we need is just a normal timer because we are there full time. The timer will be able to execute the predefined time. Okay, and also I want to put the similar the delay at I3 so that it can pass that point of I3 a bit, unlike stopping immediately. Keep in mind that these timers currently they are just cosmetics. They're not that important to our circuit anymore. Alright. Okay, now the workpiece passes the sensor a little bit and it comes closer to the end of the conveyor. And then I've realized that also at the I4 here deserves a delay also because it this one here it rushes to come down, so I need it to delay just a little bit. Actually, coming down is not a problem. Going up is a problem. So at here, I'll just put a delay here. Okay. Just to delay the upward motion. Okay. And all right, let's see now. Before I forget, another important thing to do is to label the state of your inputs. Normally closed, the sensor. You can just say forward sensor. I prefer the bold. Okay. And then I3 normally closed, backward sensor. This one normally closed, high level sensor or switch. And this one is a low level. Low level switch. So you need to, this is well used by the people who will be interacting with your machine. They need to know these labels. It will help them to identify them. Firstly, the location and the state of your inputs, whether they're normally closed or normally open. Start button most of the time it's normally open, and the other thing is I didn't include the stop button functionality because I believe that when it comes to real machines you need to stop the machine using the safety PLC. So safety PLC is a PLC dedicated specifically for stopping the power that goes onto your motors, your yes, your motors in particularly, and uh, your output specifically. Yeah, so it controls the outputs, and it makes sure that it cuts the power that goes to the outputs using a emergency stop button, because your outputs are your the likes of your, say in the CNC, the chuck is rotated at a higher speed, and it's very powerful, so it can just pull you into the machine. You have big motors that are rotating, fans, pumps, and things like that. At times, things can be a bit dangerous, therefore, you need a dedicated uh, system that will make sure it's designed to stop those types of systems. So therefore, if you would want to put stop button, you can, but it will affect the nature of your program. Therefore, to remain with this program, you would have to install a safety PLC, or even a second PLC will still work, but it's not recommended. A PLC that will be dedicated to control your relays. So the power that goes to your relays or your contactors, you control it separately with just a simple PLC that you can be able to draw a simple program. So whenever you start the machine, you stop it, it will always stop in time without affecting this current program. All right, I think I've explained enough. So now let's see how the machine will react after we've made these cosmetic changes. All right. The delays are very important, even though you don't see them much, but they are critical. Okay. All right. So the program, it's only correct if you can do it twice. I'll first start by removing the wet piece and start it again. After 3 seconds, it goes forward. Right? Let's see how on the screen it looks like. Perfect. Thank you so much.